so these are some examples of solids here. There's a waxy solid. It's probably based on organic then, the wax crayon there. Okay, liquids. Liquids are similar to solids in as much as we call them the compact states of matter. So what do we mean by that? Well, the atoms or the particles, the molecules, are very close together. In other words, they don't take up much volume really, and they fit in a container. The difference with a solid and a liquid, though, of course, the liquid adopts the shape of the container, whereas a solid will not do that unless you ground it to a powder, of course. Okay, but it still has a fixed volume. Okay, you can't compress the volume of a liquid and you can't really expand it even if you change the pressure. And of course, it has a definite surface, an edge to that body in the same way as a solid. So in a liquid, the particles definitely must be able to slide past each other, otherwise it wouldn't be able to change its shape. And you can say, therefore, in a solid, they definitely cannot slip past each other because otherwise it would change shape. Okay, and that changing of shape gives rise to lovely phenomena like we see this waterfall. Wouldn't be possible otherwise. Okay, so the odd one out of the three, as you may have guessed, is the gas. Okay, because it doesn't have a definite edge. It's hard to define the volume because it very, very much depends on the surrounding pressure. And it doesn't have, well, it doesn't have an edge. It's just very hard to define. It doesn't have a shape for that reason. Okay, but we pretty much better understand gases because they're all around us, and respiration is extremely important in medicine and everyday life. Okay, and some of you are going to be anaesthetists, so you definitely need to understand gases, just as biomedical scientists will need to understand aqueous solutions and buffer solutions because they mimic physiological fluids and so on. Okay. So physical change is a change not in the kind of matter that it is, but in the kind of form that that matter takes. Okay, so some of these are different from the others. What have these three got in common? Have a look at the middle one there, the middle ones. So liquidize, solidify, and boil. What are those changes? What do we call those? Does anyone know? Who's not spoken yet? Attila, any ideas? How are you doing?
Yeah, so they change the state of matter.
Yep,
Those
so
three.
those are all changes between states. Yeah, what's another word for state in this case? It's a little bit more technical. Beginning with P, does anyone know? Not a state change, but Johanna?
A phase change?
That's phase change. So those are the two possible phase changes. I say two possible, those are the boundaries between solid and liquid, and then liquid and gas. So we could say there's two types, but don't forget we can have the changes going backwards as well, and they have their whole separate terminology. So you need to be familiar with those terminologies. Okay, so as I think you know, liquidize is not a word you hear much, all right? Melting is the real one you need to know. That's what people use. Okay, so that's solid to liquid, of course. Okay, and the reverse of that is solidifying or freezing, depending on the temperature, really. Okay, which is liquid to solid. So what about the other phase boundary, so between liquid and gas? So which of those two is correct, boil or evaporate? Any opinions there? Or maybe they're both correct. I think I'm missing half of my panel members here. Just trying to find the rest of you. Okay, so what's the What's the difference between evaporation and boiling? Isabel, you had your hand up.
No, I thought boil is the more usual term. I think.
They're both quite used actually, but they mean something slightly different. Dahlia.
I'm not really sure, but I'd say that evaporate is just make into gas and boil is to bring it to the point where it's hot enough that it becomes gas.
It's kind of to do with temperature, yeah. So they're both referring to liquid to gas, or vapor as you might call it as well. But it's just really the temperature at which it happens. So every liquid has its own characteristic boiling point, but it's to do with whether the change happens above or below. Yeah, Eustace. Yeah, you had a question.
Yeah, yeah, right.
Sorry, is that how you say your name?
Yeah, it's Justus, right?
Okay, great.
Yeah, perfect.
Okay.
I just got a quick question. Isn't it with boiling that I have to put continuous heat on it to make it into vapor? Isn't that a difference as well to evaporate?
You have to put what, sorry?
Heat. You have to heat it consistent that it evaporates.
Well, they both require heat input. So usually evaporation is for one that has less heat and it's occurring below the boiling point. So you wouldn't say, if there was a puddle on a rainy day, you wouldn't say the puddle is boiling after the sun comes out.
No, I wouldn't.
Unless it's a very hot day, which certainly not happen in England. Okay, so but it's a slower process. It's below the boiling point, but it's the same escape of those particles into the gas phase. So yeah.
Okay, thank you.
Thanks. Boiling is above that particular characteristic boiling temperature, so that's a constant value for every substance. Every substance has its own characteristic melting point and boiling point. Okay, and we've already talked about this. Oh, sorry, what's the opposite process, which we haven't got on the slide? Gas going back into liquid. Amit.
It's condensation.
Yeah, condensing. Yeah, good, thank you. So when a gas condenses into a liquid, yeah, it's condensing. Good. And there's a couple that we haven't seen there. So there's a few substances which go directly from solid into vapor. They don't bother with the liquid phase in between. So carbon dioxide actually does this. Does anyone know what that process is called? Who's not spoken yet? Clara? Have you heard of that one?
No, not at all. I'm sorry.
Okay, it's unusual. I mean, it's not a common phase change. It's just for a few substances under a few freaky conditions. But that's actually called subliming. And it's just one that you sort of need to know about. Iodine does it as well. You can get these lovely purple crystals and so on. Yeah. And as we talked before, we talked about dissolving as well. That's the one at the bottom. Okay, that's really important for chemists because they need to know. Johanna, you have a...
Yeah, sorry.
Okay.
Yeah, you said subliming, but
yes.
you asked about gases turning into solids, didn't you? Or was it?
I mainly asked about solids turning to gases, which is the usual way around. So, but it's a good point actually. Although I wasn't going to refer to the reverse process because gas turning directly into solid, which is, of course could easily happen, is usually referred to as like deposition on a surface, either deposition or just condensing in the same way. You could call it that as well. Yeah, good point. Dissolving, this last one in the list is really important for chemists because nearly all reactions are done in solution. It's really rare, even if it's not shown in the equation, that you would bring substances together in their pure forms and mix them because it's just too concentrated, it's hard to control. If you have heat coming out of that reaction, it's hard to dissipate the heat. So if you're synthesizing a molecule in, say, in the pharmaceutical industry, on a large scale, you're doing a drug manufacturer, you need really controlled conditions. And the best way of controlling the temperature is to put it in the medium of a solvent. So there's a lot of there's a lot of controversy about the amount of solvent that's used in terms of chemical waste. So getting sustainable solvents is one of the projects that I'm researching with my students at the moment. There's a lot of environmentally bad solvents out there which need replacing, and they slowly are being replaced. It takes time.